Hi, everybody. Thank you for coming to this talk. So I'm going to talk about an invariance principle for the multi-slice with some applications to theoretical computer science. So this is joint work with Braverman, Subhash, Khot, and Noam Lifshitz. So let's begin the talk with the most basic form of invariance principle that I hope most of us have seen, which is simply put the certain limit theorem. So let's recall what it says. So the standard limit theorem is the following type of statement. It says that if we have x1 to xn independent random variables whose mean is 0, variance is 1, and otherwise they are reasonable, say they have bounded fourth moments, then if we sum up these random variables and divide by the standard deviation of the sum, namely square root of n, then we get a random variable that behaves sort of like a standard Gaussian random variable. And I don't want to get too much into details of what I mean by approximately, but you know, you can think that these are really close distributions. But this form of statement is a bit misleading in the sense that we can rewrite it in an equivalent form, but this would give it more of a sense of an invariance. So what is that equivalent statement? Well, here it is. Suppose we have x1 to xn independent random variables as before, and now we also have g1 to gn independent standard Gaussians. Then an equivalent statement to the former is just to say that if we sum up x1 to xn and divide by square root of n, then the distribution is roughly the same as if we sum up g1 to gn and divide by square root of n. And this is really equivalent because, right, the distribution of the right-hand side is exactly that of a normal random variable. So really this is an equivalent statement, but this form of saying is a bit more suggestive. So how do you phrase this statement in invariance land? Well, what you say is consider the multilinear polynomial p of y1 to yn, which is simply the sum of y1 to yn divided by square root of n. Then if we consider the distribution of values of p, when instead of y1 to yn we plug in random variables, then this distribution of values really only depends on the mean and variance, provided of course that the coordinates are independent, because whatever you put, it's always going to be a Gaussian. Or in other words, the distribution of values of py1 to yn is invariant under the actual distribution of y1 to yn modulo that we know the mean and the variances. So how is this relevant to TCS? Well, let me tell you about that. So it all starts with a very nice paper of KKMO in 2005 that wanted to establish the following type of statement. It wanted to establish the fact that the Gomez-Williamson algorithm for max-cut is optimal. And in order to do so, it used the so-called unique games conjecture. They proposed the reduction from unique games to max-cut. And they wanted to show that this reduction shows that the Gomez-Williamson algorithm is tight. But for that proof, they needed a statement that they didn't know how to prove them, which they called the majority established conjecture. And modulo that they knew how to do things. And indeed, this is a very nice reduction and it's very influential. And later, I think that maybe 2 or 3 years after this paper, the majority established conjecture was proved. And indeed, a key ingredient, or perhaps the key ingredient in the proof, or at least the original proof, is a more general form of the invariance principle that we've just seen. So this is the following invariance principle of Mosel, O'Donnell, and Lifshitz. It's a generalization of the former invariant principle, and it says the following statement. Suppose now that we have a multilinear polynomial, py1 to yn, and we want 2 conditions. First of all, we want this polynomial to have low degrees. And by that, I mean that d is small. Think of it as constant. And secondly, we want the influences of all of the variables to be small. And I don't want to get into the technical details of what influences are. It's a very important concept in analysis of Born functions. But I suggest that you just think of it as that no variable appears in too many of the monomials. Then under these two conditions, the distribution of values of P is invariant under the distribution that we plug into Y1 to Yn. That is, if we take an ensemble of independent random variables x1 to xn and another ensemble y1 as z1 to zn, and I guarantee that the moments of x1 and z1 match, say the mean and the variance, and so on and so forth, then the distribution of values of p x1 to xn is very similar to the distribution of values of p of z1 to zn. So this is the invariance principle of Mosel, O'Donnell, and Lifshitz, and this plays an important role in the KKMO result. So this invariance principle was originally developed for TCS and for PCB, but later on it found many other applications throughout TCS and more broadly in discrete math. And a prime example of an application of it is Ragameda's result that we'll get back to a bit later, showing that SDP algorithms are the best you can do for CSPs. So the main goal of this work is to prove more general invariance principles or invariance principles for other domains other than product domains, when x1 to xn are not independent, but they may have some dependencies. So let me give you a brief overview of what we're going to see. So we're going to first define the main object that we discuss in this work, which is the multislice. Then I'll tell you a basic version of our result. I'll briefly tell you about two applications of this result to PCB. And finally, I'll state some open problems. Okay. So what is the multislice? Well, here's the definition. So suppose we have m, a natural number, say m is equal to 3, but more generally, you should think of m as some constant. And we have n, which is large. Now, if we're given m numbers, k0 to k-1, that sum up to n, then we can define the corresponding multislice. So this is v vec km, and this is the collection of all strings in m to the n with prescribed numbers of coordinate equal to each value. That is, the number of coordinates that are equal to b is precisely k sub b. Or again, in other words, this is the set of vectors in m to the n that have prescribed number of symbols for each one. And for us, we'll mainly discuss roughly balanced multislices. And by that, I mean that each of the k sub b's is not too close to 0 or too close to 1. So there's something in the middle. And sort of the meta question here is, okay, so you look at this multislice, and indeed there are some correlations between the coordinates because you have these cardinality conditions. And the question is, how different is this domain than m to the n itself? Or when is different and when is it the same? And there is a lot of motivation to study this sort of problem. So for example, oftentimes in extreme combinatorics, you want to study some problem about subsets of psi k, but then you can move to a product domain, which is easier to analyze, and perhaps do something here and transfer it back to the uniform case. And also in computer science, there are many cases in which you want to do something like that. So for this work, let us make the question a bit more precise. So the question we consider in this work is, suppose we have some function over the multislice, some really valued function. Can we find a counterpart of it, f tilde, on the product space, such that these two functions behave similarly? And I don't want to define behave similarly exactly here, we'll see it a bit later, but this is the rough question that we study. In other words, we want to establish invariance principle for functions. We want to, given a function, we want to associate with it a function on the product space such that these two functions are, roughly the same. So this question was not raised by us, it was raised by earlier works. So there were two works that have dealt with the case of the slice, which is the case that m is equal to 2. And indeed, they managed to show that such invariance principle holds for low degree functions. And here, the notion of degree will be defined shortly, but quantitatively, they show that if the degree of the function is slightly less than square root of n, then you're in good shape. You can indeed establish an invariance principle. So what is the degree? Well, first I need to tell you what a junta is, and then the notion of degree follows shortly. So we say a function is the junta if, in order to determine the value of f of x, I only need to look at most d coordinates in x. And then I say that a function is degree at most d if I can express it as a linear combination of d juntas. So this result on slice is very nice, but the techniques that they used relied very much on the case that m is equal to 2. And this is because they use an explicit basis for functions, a basis that is called harmonic polynomials. And once they derive this basis, it's a kind of basis that you can do lots of explicit computations over. And indeed, this is what they do, and they end up proving this invariance principle by force. And if you wanted to extend these techniques beyond m equals 2, you'd need to find a basis and hope that everything works out well, which may or may not be possible. They propose it as an open problem. But what we do in this work is we consider more general methods. We address the general case that m is constant and use kind of symmetry-based methods in order to get around this basis issue. So for simplicity for the rest of the talk, I'm going to consider the uniform case in which each one of the k sub b's is equal to n over m, but our results hold for more general case of roughly balanced multi-slices. So what is our result? So this is a technical statement of our main result. So it says the following. Suppose I have a function of degree smaller than square root of n. Then I can find another function, f tilde, on the product space, as well as a coupling between the multi-slice and the product space, xu. By that I mean just a jointly distributed pair of random variables where x is uniform over the multi-slice and u is uniform over m to the n. So under this coupling, when I evaluate f at x and f tilde of u, these values are very close to each other typically, in the sense that the expectation of the square root of the difference is very, very small. So this is what I mean by these functions behave very, very similarly. I hope that this is similar enough. And this function f tilde has a bunch of other nice properties that I'm not going to list, but that we also use in our applications. And furthermore, the function f tilde is derived in a very natural way from f, and you can sort of think of it as a very slight noisy version of f. So just to give you some intuition, if I take a random point in m to the n, then I know that each one of the values from 0 to m-1 is attained in roughly n over m plus minus square root of n of the coordinates, just because of some concentration bound. So therefore, u is typically kind of close to the multi-slice. So you can hope to take u, take x that is closest to it on the multi-slice, and perhaps define f tilde of u as f of x. So this is a bit too much to ask for. So instead, what you do is you take average over x's that are kind of close to it. So, and this works. But in order to analyze this, you have to do a bunch of things. So you cannot use a classical Fourier analysis, which is what people used in order to prove invariance principles typically. So this is not a product domain, so this is not available. So instead you use symmetry-based techniques, and you use basic tools from representation theory in order to make the proof go through. So as I said, this is a basic version of our invariance principles. And in the paper, we also derived more general forms of it. And in particular, we are able to establish analogs of classical results, such as majority Stelvest theorem and more general correlation bounds over the multi-slice. And to do these things, we have to do work for functions that are not of low degree, and we need to study how these things behave on the high degrees. So usually what we have to do is we have to show that the high degrees don't contribute anything. And for that, we again use more representative theory along with the trace method in order to bound eigenvalues of certain operators. Good. So let me now tell you briefly what sort of applications we show in the paper for our invariance principle. And let me begin with making a more formal statement of Braverman's theorem that we mentioned earlier. So roughly speaking, this theorem tells you that if you look at a constraint satisfaction problem, the best you can do is an SDP algorithm. And more precisely, what this theorem says is, if you have a CSPP and you take some epsilon, then there is a value S such that if I give you an instance psi of P, and I promise to you that the value is at least 1 minus epsilon, then the SDP algorithm A manages to get value of at least S and psi. And furthermore, improving upon it is NP-hard, at least assuming UGC. So this is Braverman's theorem. And what we're after here is what happens when you demand perfect completeness. Namely, what happens when you take epsilon equals 0. So I claim this is not a mere technicality. So this epsilon being greater than 0 is very crucial in several places in the proof of Braverman's theorem, but it's not a technical issue. The problem can be very, very different. So for example, if our predicate is linear equation, then the behavior for epsilon greater than 0 is vastly different than the behavior for epsilon equal to 0. Because you can solve a linear system of equations, but when it's only 99% satisfiable, then this problem becomes very, very hard. So this is really a different problem. And also, all of the techniques that Braverman use cannot be applied directly, or we don't know how to apply them. And there are various places this is used. So Braverman applies some noise in various places, which immediately gives up this perfect completeness. Also, to begin with, UGC as imperfect completeness. So yeah, this is even a non-starter. So the question is, what do you do for perfect completeness? How do you prove hardness results? So what we show in the paper is that once you replace UGC by a certain surrogate that has perfect completeness, which is called rich 2-to-1 gains, then the invariance principle for multi-slices helps, or at least in some cases. So let me give you two examples. So again, we show that assuming this rich 2-to-1 gains conjecture, you get some new hardness results for problems with perfect completeness. So the two examples that we show in the paper are for coloring, which is the following result. So it says that for every delta greater than 0, if I give you a graph G, it's NPR to tell whether G is 3-colorable or G has no independent set of size, at least delta. which is a very strong condition. In particular, it means that G is not 1 over delta colorable. So this result was not known prior to our work. And now we know it, at least assuming this reached to the 1 games conjecture. And secondly, we can show almost optimal gap of hardness for KCSP. So here we show that for certain values of K, which are powers of 2 minus 1, there is a predicate P such that it's NP-hard to, given an instance of it, it's NP-hard to tell whether the instance is fully satisfiable or at most 2K plus 1 over 2 to the K plus a little bit satisfiable. So the best gap that you can hope for is satisfiable versus 1 over 2 to the K, and this is very, very close to it. Yeah. So let me conclude this talk with some open problems. So the first kind of general question is, can we prove invariance principles for other non-product domains? So in this work, we show that symmetry really helps, but maybe other features of domain can be also used to derive invariance principles. Secondly, in the paper, we show a kind of more general result that transfers a dictatorship test to a hardness result, but we are only able to work with certain class of dictatorship tests. So it would be very nice to extend that class to perhaps facilitate a future Raghuvendra type theorem for problems with perfect completeness. And thirdly, so you know, the invariance principle originally was developed for hardness approximation, but later on found applications in many other fields. So we believe that these new invariance principles should also have applications in other fields. And indeed, in a forthcoming work, we show that you can derive some new results in extremal combinatorics using it. But this is the topic of a different discussion. So I hope you enjoyed the talk, and thank you very much for watching.